This course is about asymptotic enumeration, and the main tools will be entropy and graph containers. And let me start with some motivating examples first. In this lecture, the first focus is the collection of independent sets. So G is a graph always, and this is I, and this means the collection of independent sets in G. And do we know what is an independent set? This is a vertex set in which no pair is adjacent. Is that okay? Okay. And then we'll use I of G. So this is the size of the collection IG. In other words, IG is the number of independent sets in G. Okay. And then as the first example, let's say G is D-regular. And it has n vertices, and then say this is bipartite. And so for this discussion, we do not need the assumption that G is bipartite, but just to simplify the situation, so let's assume that G is bipartite. And as a default, we always assume that D and N, they are quite large. So you can assume that they are, like we assume that they tend to infinity, but they are finite. So they are just large numbers. And so the situation is we have this graph. And on one side, we have exactly n over 2 vertices. And on the other side, we also have exactly n over 2 vertices. So n is an even number. And then in this case, we want to think about what is the number of independent sets in this graph. So first of all, we have a very easy lower bound. This is at least 2 to the n over 2. Do we see this? Why is this true? Any young students? Why is this true? Yeah?
Take one part.
Oh, take one part? What do you mean? Take one part?
Yeah, all subsets of one.
Oh, yeah, great. Are you young?
I'm
Okay, great. Okay, so we have this the trivial lower bound on the number of independent sets. On the other hand, if we assume G is irregular on n vertices, then we have okay. So this lower bound is not so far from the upper bound. So for example, we have this pretty well-known proposition. We know that the number of independent sets in that graph is at most 2 to the 1 plus little o. That depends on D of 1 times n over 2. So this is little o, and this little o means as D tends to infinity. Okay? And there are at least 2 proofs. And one, we can use like entropy method to prove this bound. And if you use the entropy method, then this little of one term becomes big O of 1 over D. And we can also use the graph container method. And if you use the basic version of the graph containers, then I think this one gets something like 1 over root D. So we have those bounds, and those 2 tools will be our main focus of this lecture. We'll see a proof for this proposition later using entropy, hopefully at the end of this lecture, but we'll see how much time we'll have at the end. And okay, and let me give you the second example. So first of all, I want to point out that if you just look at the exponent, then this exponent is asymptotic to the exponent in our lower bound, n over 2, right? So in this sense, this upper bound looks pretty good. On the other hand, if you look at this expression more carefully, this is actually 2 to the n over 2 times. We have a multiplicative error term, which is 2 to the little o of n over 2. And if you look at this term, this is not small, right? So for example, it's possible that like this one is very, very big, very, very big, like n over d. And in that case, this error term is enormous. So in that sense, this upper bound is not really close to this naive lower bound. And our question is, okay, then what if we are given more assumptions? In that case, can we improve this upper bound? That appears in our second example. So let's use QD. What is QD? Who was not in Imre's lecture? Okay. Do you know what is QD? It's the hypercube. Okay. So, but we still have a young student, so let me explain what this is. So this is a d-dimensional Hamming cube or hypercube, d-dimensional hypercube. And so for example, Q3 is on my back here. So this looks like this. Okay, and at the bottom we have all of the zero. Okay, let me say this is 0, 0, 0, and at the top we have 1, 1, 1, and in the first, like here we have 1, 0, 0, 0, 1, 0, and 0, 0, 1, and etc. So this is the three-dimensional hypercube, and in general, when we have QD, the vertex of the QD is the binary string of length d, and two vertices are adjacent if and only if they differ on exactly one coordinate. Are we okay with this? So we have seen this before. Okay, and if you look at QD, then this is irregular. So this still satisfies the assumption over there. And also this is bipartite, right? And the bipartition is unique. It's bipartite on the partition, let me say E union O, where E means even vertices and O means odd vertices. And what does it mean by even vertex? That means this binary string contains an even number of ones. And O means the collection of binary strings with odd number of ones. Is this clear? And do you see that they form a bipartition of the hypercube? Okay, great. And then what's the number of vertices of QD? Okay, great. So this is 2 to the d, and we'll use big N to denote this number. So from now on, big N always means the number of vertices in QD. Are we okay? Okay. And then, so here in this question, for this specific example, we want to ask, what's the number of independent sets in this graph? So here, again, we have this trivial lower bound, which is 2 to the n over 2. And we have an upper bound here. But as I said, if you look at closely, then the gap between the lower bound and the upper bound are pretty enormous. And then what's the truth? And this was proved quite a while ago. So this is the theorem by Kirchhoff and Sapozhenko. From 1983, so before most of us were born. And they proved that the number of independent sets is asymptotic to 2 times root e times 2 to the n over 2. Do you know what this symbol means? This means, okay, so we use this symbol if and only if their ratio tends to 1 as d tends to infinity. Okay, so this means if d is large enough, then the ratio of this number and this number tends to 1. So you see that this is much sharper asymptotics than this estimate, because there is no multiplicative error term. It just says that this number is 1 plus little of 1 times this number. So basically, one of our target statements in this entire course is to prove this statement. And this requires more, like stronger analysis than what's used in this statement, of course, because we are aiming for a sharper estimate. And okay, and And we will not just aim for independence, so focus on the independent sets, and we want to generalize the notion of independent sets to graph homomorphisms. So eventually, we want to find sharper estimates for the number of not just independent sets, but for more graph homomorphisms. So who are not familiar with graph homomorphisms? Nobody? Okay. Young students, what is a graph homomorphism?
It's a mapping of the vertices such that the density is preserved, but
Great. Wow, wow, great. Okay, maybe you should lecture. Okay, so since everybody knows the definition of graph homomorphism, is it really true? Everybody knows the, oh, okay. So let me not write it down, but, okay. Then for example, like graph homomorphisms. So this generalizes several important notions in combinatorics. For example, if we have independent sets, let me say IG. So this can be represented as a graph homomorphism from the vertex set of G to some graph. And do we know what this graph is? This is graph with one edge and one root. And we can label them, this is 0 and this is 1. Then is it clear that this graph homomorphism gives us an independent set? This is because, let's say this is our G, like this. This is our G. And if we label this vertex with 0, then this is the neighborhood of this vertex, like this one, and this one, they have freedom to choose either 0 or 1, because 0 is adjacent to 0 and 1. So in this case, we can label them freely, like 1, 1, 0, like this. On the other hand, because this vertex is labeled 1, so that means this vertex must be labeled by what? 1? No, 0. Why? Because 1 is not adjacent to 1. So it's only allowed to be labeled by 0. Okay, so this graph, this target graph, gives us the graph of independent sets. On the other hand, another example is when we consider, can you see here? When we consider proper colorings. So let me say proper colorings with Q colors. Yes? Oh, of course, yeah. How about this? Thank you so much. And yeah, I think it's okay now. Okay, so in the second example, proper Q colorings can be also represented as a graph homomorphism. And in that case, what is our target graph here? Proper colorings of the vertex at G, of G, can be viewed as a graph homomorphism from the vertex set of G to where? Yes, it's complete graph on Q vertices. So let me say KQ. This is the complete graph on Q vertices. This is okay, and this is because, so again, if you have a graph like this, so let's say we color this vertex with color 1. In that case, it's neighborhood. They can pick any color but 1, because 1 is adjacent to any other vertices but 1. So this gives us a graph coloring. Okay, and another example is a Lipschitz function. So in this case, if we set our h to be the integer line, z, and we have integers, and then we add some loops like this. And do we see that in this case, a graph homomorphism corresponds to an integer valued one Lipschitz function? Do you see that? This is because, again, if we have like a graph like this, and if we assign number 0, for example, to this vertex, then those vertices must be either 0 or 1 or -1. because otherwise, because this 0 is only adjacent to 0, 1, or minus 1. Okay? So this graph gives us an integer valued one Lipschitz function. Is that okay? So those are just the examples that shows that lots of interesting objects in combinatorics can be expressed as a graph homomorphism. So eventually, we'll try to extend this statement to counting graph homomorphisms, or more specifically, maybe counting graph colorings on a specific graph. And we are aiming to get sharper asymptotics in that case. Okay, so when we have an independent set, if this, so if vertex is in I, then its label is 1. And if V is not in I, then its label is 0. Is this clear? Are you sure? I see some frowning face.
Yeah, I think I get it.
Oh, okay. So basically, if we have a graph and if we have some independent sets, then the usual convention is we label the vertices in the independent set by 1, and we often say that they are occupied. And then the vertices outside of the independent set, they're labeled by 0, and we usually say that they are not occupied. Is this clearer?
Yes.
Okay, question?
What's meant by one Lipschitz function on the graph?
Oh, okay, one Lipschitz function, that means if you have a graph, and if V and W are adjacent, then f of V minus f of W is at most 1. This is definition of a one Lipschitz function on a graph.
And f maps into integer.
Yes, integer valued, yes. So f is from the vertex set of G to the integer, such that which satisfies this condition.
And you construct a homomorphism into that 0, 1, minus 1 graph?
So I'm saying that there is a bijection between the collection of graph homomorphisms to this graph and the collection of one Lipschitz functions on the given graph. Is this fair? Okay, great. Any other questions? Please ask me questions. Yeah, I know that I'm confusing you, so. Are we okay? Okay, great. So those are some examples of graph homomorphisms. And now I want to move on to our tools. So as I said, we have some statement, and it's already gone. So we had a statement on the asymptotic number of independent sets in the regular graphs, and the tools that we can use to prove the statement is either entropy method or graph container method. And my plan for the rest of the lecture is to introduce entropy basics and then prove that statement using entropy. But I'm not sure if we'll have enough time, but let me try. So let's first discuss entropy basics. I know that many of you have seen this before, so in that case, you can do your work. And I'm explaining for more like younger students who haven't seen this before. So in this setting, x and y, they are discrete random variables. RV means random variables. And we'll use P of x for the probability that x equals x. And our log is always log base 2. Okay, and let me define the entropy of x. So the entropy of the given discrete random variable x, this is defined to be h of x, is summation for all of the x and the probability of x times log 1 over the probability of x, where this sum is taken for all of the x's in the support of x. Okay? And usually, conventionally, we say 0 log 1 over 0. This is defined to be 0. But in this sum, we only consider the value of x's where p of x is not 0. Okay? Then why do we care about this expression? So informally, we say that this h of x measures the amount of randomness or surprise or information in the given random variable x. So for example, this function has very nice properties. And the first property is we know that the entropy of x is always at most log of the size of the range of x, where the range means the collection of values where for which the probability of x is not 0. Okay, so basically range is the values that x takes with a non-zero probability, and this one becomes equality if and only if x is uniformly at random. Okay, and why do we have this? So here we'll discuss several properties, and I will leave most of the proofs as an exercise for the problem session. But let's briefly try to prove the first property. So this is because the entropy of x is, summation x, p of x, log 1 over px. This is a definition. I just copied the definition from the board on the left-hand side. And if you use Jensen's inequality, then we can move the summation inside the log function. So that means we have log, and this is because log is concave. This is log summation x, probability of x times 1 over probability of x. Do you agree with this? Have you seen Jensen's inequality before? Okay, great. So, and then what we have here, so this is 1. So in this summation, 1 is counted as many as the size of the range of x. So the conclusion follows. And I think this briefly gives us why entropy it can be viewed in this perspective, because so this says that if x has more values in its range, then the entropy of x is larger. So for example, if we have two dice, and one die has 6 faces and another die has like 1,000 faces. In that case, whose randomness is greater? You can say that the second, like informally, or intuitively, we can say that the second one has like more randomness. And also, like the equality is achieved when x is uniformly at random, and we can say that uniform distribution is more like the most random. Because when we have a coin, biased coin, which has probability for a head is 0.999. And in that case, we can hardly say that this coin is very random. On the other hand, when we have a fair coin, then it can be viewed to have a more randomness than the biased coin. So in that sense, when x is uniform, it's most random. And so that gives this, and so that maximizes the entropy in x. Are we okay? Okay. Any questions? Do we have any questions, or is this too easy? Okay, let me move on. And then I'll just state some of other well-known properties. So first we have, if we measure the entropy of several random variables like this, then this is at most entropy of x1 plus ... entropy of xk. Again, in terms of randomness, if we measure the randomness of all of those random variables collectively, then of course this cannot exceed the randomness for each individual random variables. So for example, if x1 completely determines x2, in that case, like adding them one by one is redundant. And we want to make this inequality more tight. So for example, we want something like entropy of xy is equal to entropy of something plus entropy of something. So we want some equality instead of Roux's inequality. And in this case, what we can do is to expose the randomness in x first, and then we look at the randomness left in y, given we already have information about x. So we want this, and for this, we need the right definition for this conditional entropy, and we define this now. So for this, we need some preliminary, some definitions. So the first definition is conditional entropy given an event. So in this case, T is an event. This is not a random variable, but this is a this is a fixed event, and we define the entropy of X given the event T using the conditional probability. So this is a very natural definition. This is the conditional probability of X given the event T, and log 1 over the conditional probability of X given T. Okay, so I believe this is natural. So conditional probability given an event is defined using the conditional probability. And then what if Y is a random variable? In this case, how can we define the conditional entropy? In this case, the conditional entropy is just the expectation of the conditional entropy given Y equals a given value. So let me write it down. This is the expectation of the conditional entropy of X given Y is fixed as Y. Okay, and then we take the expectation, and then what is this? If we write it down, then this is summation Y, probability of Y, and entropy of X given Y equals Y. So we just take the expectation. Is this okay? So we first defined the conditional entropy given an event, and then next we defined the conditional entropy given a random variable as the expectation of the entropy given the event Y equals a certain value. Okay, so this is basically the expected amount of entropy for given the value of random variable Y. Are we okay? Okay. And the third basic property using the conditional entropy is this. So entropy of X and Y, this is exactly entropy of X plus entropy of Y given X. And again, Bob put it in the problem section, and you can think about this, how to prove it. And in general, if we have multiple random variables, then we can expand this expression. So entropy of X1 plus entropy of X2 given X1 plus entropy of X3 given X1 and X2 plus dot, dot, dot. We can do this at the end, through the end. Okay. And finally, number 4, not finally, we have one more. If Y determines the random variable Z, then if we compare the entropy of X given Y and the entropy of X given Z, then something is smaller than the other. Which one should be smaller? With the intuition that entropy of X is the amount of randomness in the random variable X. So if we compare this, and this Y determines Z, which one should be smaller? Which one should contain less randomness or less information? Who thinks it's the left-hand side? Who thinks it's right-hand side? Oh, okay, half and half. That's amazing. Okay, who thinks they are equal? Nobody? Okay, so we have this. And this is because Y determines Z. That means Y gives us stronger, or more information than Z. So that means because we exposed more information, bigger information, so we are left with less randomness. Is this intuitively okay? And you can actually prove this using the definition and Jensen's inequality and etc. Okay, are we having fun? The last thing is pretty well-known inequality about entropy, which is called Shearer's lemma. And let me give you one example of the implication of this lemma first, and then I'll give you the statement. So this is basically the generalization of number 2, right over there. And one example, or one implication of this lemma is this. Let's say x consists of 4 random variables, x1, x2, x3, and x4. And in this case, of course, we know that entropy of x is at most entropy of x1 plus entropy of x2 plus dot, dot, dot. We know that from this property. And Shearer's lemma gives us something more than that. So it says that this is at most, for example, 2/3 of entropy of this plus 1/3 of entropy of x1, x4 plus entropy of x2, x4 plus entropy of x3 and x4. So if you look at what happens here, then you see that if you look at x1, and if you look at their coefficients, then their sum is exactly 1. So that means the weight of the entropy of x1 is at least 1 on the right-hand side. And you see the same thing happens for x2 and x3 and x4. If you sum up their coefficients, then it's almost at least 1. It's actually exactly 1 because I made it up, but we just need the sum of the coefficients to be at least 1. And does this make sense? So basically this means we cover each component of this random variable by at least once. So if you look at the sum of this entropy for the groups of random variables, then it gives an upper bound on, on the entropy of x. And you see that, do you see that this is a special case of this? Okay, and the formal statement is this. Let's say, okay, this is lemma. So x, let's say x is x1 dot 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 xk. This is a random vector. And let's say we are given a weight function alpha defined from the power set of k to r. So what is this? So, okay, notation, this is the set of integers from 1 up to k. And this is the collection of subsets of this set. So the weight function is defined on the power set of k. And the assumption is if for each I and A's containing I, the sum of weight is at least 1 for each I in our set K, then we have this conclusion. So the entropy, can you see here, if I write down here, entropy of X is at most the sum of the weight function times the entropy of this, where this means xi, where I is in A. So let's take a moment to appreciate this lemma. So I gave you this example first because this example basically shows what happens here. So what happens here is, so we want to give an upper bound on the entropy. And what happens on the right-hand side is if you look at each element I in, if you look at each xi, and if you look at the sum of its coefficients like this, then their sum is always at least 1 for all of the xi's. And in this case, the summation of this, the weighted sum of the entropy of the groups of random variables is at least the entropy of x. Is this okay? Okay, and again, basically this generalizes what happens in this example. Okay, so I think we are now ready to prove our proposition. And let me erase this. By the way, in the proof of this statement, we'll need a lot of properties that we have discussed so far. So do you think your memory is strong enough to memorize all of the properties that we discussed so far? Okay, great. So the target statement is the proposition that if G is D-regular and on n vertices, and this is bipartite, then the number of independent sets is at most 2 to the 1 plus big O of 1 over D times n over 2. Big O of 1 over D means some constant times 1 over D. And the starting point which I think is really important is this. Okay, so this starting point basically connects this enumeration problem and the entropy technique. So what's the connection between the entropy technique and the enumeration problem? So if we consider F from the collection of independent sets, and we pick this uniformly at random, then what can we say about its entropy? If you still remember the property, if you haven't seen this before. So if we pick F, a random independent set, uniformly at random, in this case, what can we say about its entropy? So we said entropy of X is at most log of range of X. But if X is uniformly at random, then this inequality becomes equality. So that means this is exactly equal to log of I of G. Okay? So now we see the connection between entropy and the number. So in order to get this upper bound, all that we need to do is this. It's enough to show that the entropy of F is at most this, the exponent, 1 plus big O of 1 over D times n over 2. So this is our target statement. And we'll prove this target statement using the various properties of entropy. Okay? Great. Okay, so we need some setting. We view F. So F is a random independent set. And this as a function from the set of vertices of G to the values 0 and 1. And we already defined this earlier in this lecture. So 0 means it's unoccupied, and 1 means it's occupied. Are we okay with this setting? Okay. And then the notation that we use. So we'll write f sub x as the value of the vertex x, just to simplify the notation. And if we have a vertex set A, then we'll use f sub A and f of A. They are very different. F sub A means we look at the values of fx as a sequence or as a vector. And this means we look at this value as a set. So what's the difference between the two notation? This one means we have the full information about the color of every single x, individual x. On the other hand, this one means we only look at the color that x uses. Color means 0 or 1, the assignment. The color of x as a set. So in particular, this one has only 3 choices, either 0 or 1 or, yes, 0, 1. On the other hand, this one contains enormous amount of information if A is large. Okay? And informally, we'll call this palette because this is a set of colors. Okay, so 0, 1, they are colors, right? They are not numbers, they are colors. Okay, and then finally, we'll use n sub x for n of x, the neighborhood of x. Okay, so let's start. So our goal is to analyze this expression, h of f, the entropy of f, using various properties of entropy. So first of all, the basic intuition is this. We have this bipartite graph with n over 2 and n over 2 vertices. And we want to reveal the colors of each vertex in a clever way so that we can reduce the amount of information that we have to reveal, or we can give an upper bound on the entropy. And one natural way to approach this is instead of opening or revealing the colors at random, we look at one part of this bipartition, and then and then reveal the other part or determine the color of the other part based on the information that we already got from the other part. Okay, so this is the approach that we use. So that means this can be written as entropy of, let me write, this is y and this is x. This is f sub y plus entropy of f sub x given f sub y. So this means we reveal the colors of y first, and then we look at the colors of x, given we already know the colors of y. Okay? And then this is equality because we are using the conditional entropy. Okay, so to get this upper bound, we just need to do two things. First, give an upper bound on the first term. Second, give an upper bound on the second term, and then combine them. That's what we are going to do. So first, let's give an upper bound on the first term, the second term, sorry. Which one do I want to do first? Okay, the second one. So for this one, we use some properties. So first of all, this is the vertex set of x, and we'll just split them. And then express this as a sum for each x in x, and entropy of f sub x given f sub y. Okay, we just split the random variable, and it never decreases the amount of randomness. Okay, and then for this one, so now we are looking at the color of x, and for this, we don't need to know all of the y's. This is too heavy tool. What do we need to determine or to specify the color of x? We just need its neighborhood. We just need to know the information in its neighborhood. Yes? I can't hear you. Did I switch something? I cannot hear you, sorry. Are x and y fixed? Oh, okay. Maybe I confused you. X is this part, y is this part. X and y are not random variable in this proof. X is just this part, y is this part. So we just named one part x and named the other part y. Does this answer your question? Yeah, x and y are not random variables. So sorry, I confused you again, as always. So are we okay so far? And then do you believe that this is at most summation x in x, entropy of f sub x, given entropy of the neighborhood of x? And we just need to look at the palette. We don't need the entire information of the neighborhood. Do we agree with this? And do we agree that this inequality is in the right direction? So okay, this is the upper bound for the second term, and let's look at the first term. So we want to think about the entropy of f of y, and for this one, we'll use Shearer's lemma. And let me just write down the result first, and then let me convince you. So this is at most using Shearer's lemma, 1 over d times summation x in x, entropy of f of neighborhood of x. So this is the result of applying Shearer's lemma, and this is because, so this is y and this is x, and now we look at this part, and we group this, or we cover the part y using the neighborhood of each vertex in part x, like this. And then we consider the entropy of each group, where each group consists of the neighborhood of a vertex in x. Okay? And in this case, why is it reasonable to have, or why is it correct to have 1 over d here? This is because each vertex in this group is covered by exactly d times. So if you are here, then by this neighborhood, this is covered by exactly d many times. So if you multiply 1 over d, then this is enough to get the sum of coefficients to be 1. Okay? Yeah, I see many nodding faces, so let me continue. So if you're okay with this, then now we write down this, we will expand this term. So this is the entropy of the color in the neighborhood of X, and we want to split this. So we want to reveal, okay, our plan is to reveal small information at the beginning, and then take advantage of this small revealed information to get a bigger information in a cheap cost. And for that, for this entropy, we'll first reveal the palette, and then specify the actual colors based on the information from the palette. So this is equal to 1 over d summation, x in x, entropy of f of the palette of the neighborhood plus entropy of f of the actual color assignment given the information about the palette. So again, what happened here is instead of looking at this information at once, we first reveal a small amount of information, which is the palette. Okay, so as I said, this one is much cheaper than this one because it only has 3 choices. So we reveal this information first, and then we look at the rest of the information using this conditional entropy. So why is it helpful? Eventually, they will be helpful if you combine this thing and this thing together. And let me write it down. So this one is at most. So now I'm combining all of the bounds. So this is at most summation x in x, 1 over d times entropy of f of the neighborhood of x. So we reveal the neighborhood of x first, and then based on this information, we specify the colors of x and its neighborhood. So this is entropy of f of x given the palette plus 1 over d times the entropy of the neighborhood given the information of the palette. So here, nothing technical happened. I just moved those things to here. And what it says is this amount is bounded above by the summation for each vertex in x part. And then we first reveal the palette, but this is divided by d because we applied Shearer's lemma. And then next, we reveal the color of x and its neighborhood based on the information of the palette for the neighborhood of x. That's what's happening here. Okay? And why is it helpful? So we do not have time to finish this completely, but let me just explain what's happening here. First of all, this is really nothing. Do you see that? Young student? I'm sorry for calling you. Okay, so this is really nothing because, as I said, palette has only 3 choices, right? So that means, what's the entropy of this palette? It's at most a constant. It's actually log 3, at most log 3. So combining with this 1 over d, this one becomes big O of 1 over d. So this corresponds to this thing. So this is really nothing. And then we have this. Now, why is it helpful? Again, the key point is we consider x and its neighborhood together. And that really gives us the powerful consequence. For example, if we consider the x and its neighborhood together, there are 3 possible cases for the neighborhood. It's either all 0, or all 1, or 1, 0. Do you see this? On the other hand, if you really have this, if the neighborhood is all 0, then how many choices does x have? You can be brave. It's either 1, 2, or 3. How many choices does X have? Yeah, it has two choices, either 0 or 1, right? On the other hand, if the neighborhood is all 1, then how many choices does X have? Just one choice. Oh, great. You're getting more brave. OK, and if the neighborhood X is 0 or 1, then what's the possible choice for X? It's 0, right? And in all cases, the entropy for the combined entropy cannot exceed 1. Because if you have 0 choice, then the entropy is 0. So in this case, the entropy comes from, the non-zero entropy comes from this part, which is 1. If we are in this case, then everybody has 1 choice, which means the entropy is completely 0. In this case, this one has 0 entropy. This one has entropy 1 because it's log 2. But each vertex has entropy 1. So that means altogether, the sum of entropy is actually D. But we divide that by D. So in all of the cases, the entropy, let me say this is star, and this is star. Star part cannot exceed 1. This is a rough description. We need some rigorous argument, but this is the reason why it's very helpful to consider X and the neighborhood of X altogether, because it gives us a restriction on the color choices for each part. Because otherwise, if you do not have this, then X can have 2 choices, and the neighborhood of X can also have 2 choices. In this case, we cannot achieve this upper bound, right? Because in this case, the entropy is 1 plus 1 is 2. So it's really good. It was a really good point, and I think we'll have to stop here. And thank you so much.